So far, we have covered the fundamental principles of designing a reinforced concrete member subjected to torsional load. The member is designed on the basis of a thin wall box section. There are longitudinal reinforcement, torsional link, as well as concrete. The longitudinal reinforcement and the torsional links takes the tensile stress, whereas the concrete takes the compressive stress. An imaginary truss model is assumed, and then based on the torsional load applied onto the member, there will be shear flow. This shear flow are considered as the external load acting into the middle through derivations of the trigonometry, as well as the fundamental principles for the derivations of the forces in reinforcement and concrete. The derivations process for longitudinal reinforcement, for the torsional link, and also compressive strut have been discussed. By putting all these three together, this establishes the fundamental principles of the design of a member subjected to torsional load. To make it simple, it consists of three basic steps. First, you need to check the torsional moment against the compression limit of the compressive strut. Make sure your torsional loads does not exceed your maximum torsional moment capacity, as represented by the diagram here. The torsional load here can be determined through analysis of the structure, whereas the maximum torsional moment is calculated using this formula, which we have derived previously. If you want to know more detail about the derivation process, you may refer to our previous video. This will be the first step here. Make sure this pass before you proceed with the subsequent steps. Why is it so? If this requirement fails, that means the section is likely to fail due to crushing. Where will the crushing happen? It happens at the compressive strut here. The crushing of concrete leads to brittle failure. This can be rather dangerous for a typical structural element. We prefer ductile failure over brittle failure, as ductile failure provides us warning in case of excessive load for the survival purposes. Now, if you find that your ultimate torsional moment is greater than the maximum torsional moment, you will need to revise the dimensions that you propose for the member. Be more specific, you will need to increase the effective area of the hollow section. This refers to the effective area here. You have two options, either by increasing the height or increasing the width. Or you may also look into the components of the formula, increasing the effective width of the section, which is this, or increasing the concrete grade will also be helpful. In the equations, you also see this data here. It was mentioned that the data should be between 22 degree to 45 degree. However, we have not mentioned that how do we get the data. You cannot simply assume the data, which is the strut angle. Normally, when you design for the torsion, you will need to check also for the shear. Especially, you have the tendency that using the shear link, also at the same time, it is a torsional link. Now, if you could recall the design process for the shear reinforcement, there is a process for you to determine the angle of the compressive strut. You will test the angle by comparing against the maximum shear resistance of 22 degree and maximum shear resistance of 45 degree. If it is more than 45 degrees, you need to redesign the section. If it is less than 22 degrees, you will assume as 22 degrees. Now, if the shear load is greater than the 22 degree but less than 45 degree, you will need to use this formula for you to determine the exact angle of the compressive strut. I hope you can still recall this calculation process. If you wish to know more, you may refer to the chapter 5, which provide a detailed explanations on how do you obtain the angle. Now, during the design for the shear reinforcement, the angle has already been obtained. Since later in your detailing, your shear link shall be used together with the torsional link, based on the principle that torsional reinforcement is to be added to the full bending and the shear reinforcement required. That means whatever amount shear link that you have calculated in the shear design, you will need to top up with the areas required for the torsional link. Ultimately, it will give you the final arrangements of the link for the section. Now, when the link here are used both for shear and torsion, theoretically, the angle here should be the same. Therefore, we will use the same angles that you obtain from the shear design while adopting the formulas for the torsional design. Same goes to the subsequent equations. Now, once you have done checking this, it shows that the sections has sufficient torsional resistance, taking the torsional loops acting onto the member. Then you may proceed with the following calculations using this formula. Where do you get this formula? This is obtained from the derivations of the imaginary truss model. Just that you need to rearrange the formula. Move the spacing to one side, and then move the design strength and partial factor of safety to the other side. Rearrange it, leaving you this formula. Bear in mind that this area here is referring to one leg of the link due to the assumptions of the model here, which you derive from one side of the member here. Having the link going something like this, if you are only designing for one side, that means you only refers to one leg of the link. This approach is slightly different with the design for the shear link, which the models assume that two legs are contributing, as the models is analyzed on the basis of the entire section. So later, when you need to sum the total area of the link up, make sure you do some simple conversions between single and double leg for you to finalize the links to be provided in the member. After that, you will proceed with using these formulas to determine the longitudinal reinforcement. Again, use the data as obtained from the shear load design. And where does this formula comes from? It comes from the derivations process of the imaginary truss model, which we have discussed in our previous videos. Rearrange the formula by moving these two to the other side, and you get this formula. Based on the amount of reinforcement bar that you have obtained, remember it is to be added up with the bending moment reinforcement before you finalizing the reinforcement in the member. And then while detailing the reinforcement, there are several rules that you need to comply with. First, you need at least one longitudinal bar at each corner, and then the amount of reinforcement bar calculated for the torsional resistance are to be added up on top of those required for the bending moment. And then the spacing between the reinforcement should not be more than 350. You can have reinforcement for the torsion lay along the member over the cross-section, regardless tension or compression zone. This is because torsional crack can happen anywhere in the member, regardless of the tension or compression zone. Whatever reinforcement that you need to place for the bending must remain, while the longitudinal reinforcement that are meant for torsional resistance, you can distribute them over the section. Alternatively, if you do not wish to distribute those longitudinal reinforcements, you can simply add up the size of the reinforcement bar, which are meant for the bending moment resistance. Either way will do. Just that when you do the arrangements of the reinforcement, make sure they are placed at the inner periphery of the torsional link. As for the link, you will need full anchorage close link, so that its contributions in resisting the torsional crack is effective. You are not recommended to use this kind of link, which are typically used for the shear reinforcement. Now, if you know that your sections is meant to take the torsional load, instead of using this kind of link, you should use this kind of link for better anchorage with concrete and more effective control of the torsional crack. And then the spacing of the link you need to control. The requirement here is the spacing between the link should not exceed the perimeter of the box sections divided by 8. We are talking about this distance. This explains the basic principles of designing a torsional resistant member. Having this basic principle understood, in our following videos, we're going to discuss about the actual applications for the design of the torsional resistant member, especially when the torsions is in combinations with the bending and also shear stress, which is most likely the case that you encounter in reality. Due to the considerations of the bending and the shear stress, the basic design process for the torsional resistance would be slightly modified. Stay tuned and I'll see you in the next video.